didn't say 1400 or 1415, so that's about. But it looks like people are expecting the presentation to start 14 from like a kind of midway. Okay. Very good. So welcome everybody. My name is Joan Carreres. I was the supervisor to this thesis. I'm very glad to have the opportunity now to see how the results look in a big screen. Very well. Now I don't remember how was the instruction for length presentation.
There was no end time listed.
Okay.
I thought you guys wanted to listen to
So glad we have only one presentation today, so it's not such a tight schedule. And then we have an opponent. Who is the opponent? Very good. So looking forward to ample time for discussion.
You guys can sign it if you like. Thank you everybody for coming today. It really means a lot to me that you all showed up. My thesis is the effective Sphagnum cover on greenhouse gas evolution and decomposition-chain exoenzyme activity of Arctic thermokarst peat. So our goal was to determine the role of Sphagnum cover on greenhouse gas evolution from pulsomyers and explore its potential contribution to thermokarst climate feedback effects. We have explored the dynamics of the microbial decomposition chain and by conducting exoenzyme assays that help identify which processes are affected by sphagnum presence, and measured methane and carbon dioxide evolution by analyzing dissolved gas concentrations in the water column. The results of this study will illuminate the potential repercussions of anthropogenic climate change on Arctic ecosystems characterized by permafrost, and aid in modeling climate feedback effects caused by pulse collapse. And this is one of our sampling sites, Itä-Palsa, in the vicinity of Kilpisjärvi, Finland, which is quite north. This is my supervisor here, Dr. Teemu Tapelainen, and our colleagues from Hokkaido University who were great help to me in collecting my research samples. My introduction is broken into northern peatlands, the definition of Arctic pulsomyers, pulsum peat composition, and biochemistry, the enzymatic latch hypothesis, our own hypotheses, and the objectives of this study. Peatlands are ecosystems with or without plant cover that have a naturally accumulated peat layer at the surface. Accumulation of peat, and therefore its carbon storing capacity, is greater at northern temperatures because the temperature allows for plant growth. Peat, of course, is just mostly accumulated dead plant matter, but the temperature is cool enough to slow microbial degradation. Peatlands in the global north are estimated to hold 550 petagrams of carbon, which is about a third of the global carbon store. So they are exceptionally important carbon sinks. Peatlands collectively account for the largest terrestrial carbon pool, so understanding their contribution to climate feedback is really quite important. Arctic pulsomyers themselves, it's a subarctic ecosystem. The peatlands rich in carbon, and they account for roughly 20% of permafrost area across the northern hemisphere. Pulsomyers are in the margin between boreals and the Arctic, characterized by discontinuous permafrost, where you have accumulation in peat mounds that have frozen peat and mineral soil pores. The warming climate is causing permafrost melt and pulsar mount collapse. Because of this, these ecosystems are critically endangered by, as evaluated by IUCN criteria. So organic matter found within pulsar peat will vary depending on plant community, local geology, and historic climate variation. Nutrients in peat tend to be vertically stratified, and the older the peat, the more mineral content and more complex, less labile recalcitrant materials will accumulate, in part because of hypoxia, but also because of exposure to mineral-rich groundwater. Thermal and hydrological fluctuations are known to alter peat ecosystem chemistry. And the biochemistry is a bit complicated. Chemical change in the environment is mobilizing, or has the capacity rather, to mobilize ancient carbon stores, which may result in detrimental climate feedback effects, and that is our concern in this study. important compounds are phenolics, phenol oxidase, which is one of the very few enzymes that can degrade phenol, and hydrolytic enzymes, which are required for the degradation of humic organic matter. And this is phenol by itself, which fortunately rarely exists alone in nature. It's almost always attached to a larger molecule. Phenol is quite toxic. So phenol alone, I should say, is quite toxic, and it's weakly acidic when attached to a carbon group. This here is a phenolic compound, and the R just signifies that there's a larger carbon organic molecule attached to it. And this shows the simplified oxidation reaction to make something biochemically useful. This is a quinone, and it's quite common in plant tissues. Menaquinone is something that is common in plant biochemistry. So phenol can be used, but it requires this phenol oxidase or another enzyme that can degrade it into something useful. This is the enzymatic latch hypothesis that describes the oxidation of phenol and phenolic compounds into other things in peatlands. I tried to make it as simple as I could here. In oxidative environments, this is what happens. We have phenol oxidase activity. Phenol oxidase requires diatomic oxygen to function, so it doesn't work the same way, it doesn't work well at all in anaerobic conditions. So without oxygen, we have low phenol oxidase. In aerobic conditions, it functions well. With phenol oxidase, phenolic compounds are degraded, so hydrolase activity, which is required for breaking down other organics, is uninhibited. And when it is uninhibited, hydrolases are able to break peat materials down into humic inorganic material, which can then be used as a substrate for microbial degradation, and greenhouse gases are evolved. So high phenolic concentration high phenolic concentration that is not degraded by phenol oxidase. Phenol tends to suppress hydrolase activity. So when there is high phenolics, low phenol oxidase activity, low hydrolase activity, this humic inorganic material is not so easily transformed into greenhouse gases by microbial degradation. So that is why older peat layers, the lower, deeper peat, does not function as much of a source for greenhouse gas evolution. I hope that makes sense. Our hypotheses. First, that sphagnum will inhibit exoenzyme activity and therefore decrease greenhouse gas evolution by phenolic inhibition. Sphagnum itself exudes compounds like sphagnol, sphagnonic acid, and other phenolics. Our second hypothesis, that sphagnum will generate a priming effect by stimulating the decomposition chain with new, fresh, labile carbon material, and that will be a source for methanogenic metabolism. The third hypothesis is that sphagnum will physically block gas exchange. So it'll block oxygen concentration in the water column, it'll block efflux of greenhouse gases, and just prevent the gas exchange between the water column and the atmosphere, which will therefore lower the oxygen and redox reactions as a consequence. The objectives of this study were to explore the biochemical effects of melting permafrost on sensitive Arctic pulsamire ecosystems, to determine the role of sphagnum cover on carbon dioxide and methane evolution from these new thermokarst pools, to understand the sphagnum effect on phenolic concentrations and exoenzyme activity, and to relate these findings to greenhouse gas production, to illuminate the potential repercussions of anthropogenic climate change on Arctic ecosystems, and to provide data for future studies endeavoring to model climate feedback effects caused by pulsar collapse. And here, this figure to the left here is a thermokarst pool. So this is what happens when we have a permafrost core that has begun to melt into the pool. The water has nowhere to go in this ecosystem, and you can see there are a lot of dead and dying plants here that have begun to degrade and decompose, and there's no vegetation covering the water just yet. This was a different site, and this at one point was raised well above the landscape, but it has now collapsed kind of in onto itself. The thermokarst pool within this collapsed ring here is starting to fill with sedges, not sphagnum, which is another potential effect. It's important to note that these ecosystems are in transition right now. They're not really stable. They're changing in ways that we're trying to predict or model. But this is unprecedented, the amount of melt and the amount of change that is happening in fossil ecosystems right now. But when we took our samples, the newer samples came from up here. Older samples came from closer to the water column here. But it's important to note that all of them now have very suddenly been exposed to water, to oxygen, to air, and some of these layers are thousands and thousands of years old. Materials and methods are broken into samples and simulation. Our monitoring measurements, phenolic assays, phenol oxidase and hydrolase assays, and finally our greenhouse gas evolution study. Our samples were taken at 4 different process sites near Kilpisjärvi, Finland. 4 about 0.75 liter samples were taken at regular depths, 5 liters of thermokarst water, and a Sphagnum culture. And we constructed open-top thermokarst simulation chambers out of PVC piping about 40 centimeters tall and 10 centimeters in diameter. And we had 4 simulation chambers per sampling site. Each had either a top or bottom layer of peat, and then each top layer we had sphagnum cover or no sphagnum cover, each bottom layer sphagnum cover, no sphagnum cover. And here on the left we've got, as we were constructing anyway, the simulation chambers, we kept them in refrigerators to keep the temperature constant, and had a lighting system over top, and the goal was to simulate the conditions in Kilpisjärvi. And here, thanks to Rose Asgard, who's not here today, but she took this picture for me as I was constructing one of our simulation chambers out of a PVC pipe. The monitoring measurements were taken at regular intervals. The chambers were kept at about 9 to 13 degrees Celsius to emulate late summer field conditions in Kilpisjärvi. The pH is naturally quite acidic. They were generally between 3 and 4. Redox potential is a measure that indicates oxygenic activity. It increased after our sampling disturbances because anytime we went in there and took a peat sample or a water sample, it would introduce oxygen, but we did our best to keep that from disturbing the samples too much. Phenolics. Water samples were taken from our simulation chambers and vacuum filtered. They were done in triplicates. We used 320 microliters of sample water and 48 microliters sodium carbonate solution, 16 microliters of Fulman's reagent, which is a fluorescent reagent to help us visualize this in the spectrometer. Standard curve was prepared with 1, 2, 4, 6, and 10 milligrams per liter phenol solutions, and then the same sodium carbonate and phenol reagent treatment. We pipetted everything into a microplate. It was incubated at 13 Celsius and agitated for 30 minutes. Absorbance was analyzed in our spectrometer upstairs at 750 nanometers. The phenol oxidase assay, we took about half a milliliter of peat from each chamber, and the samples were homogenized and placed in pre-weighted Eppendorf tubes. 750 microliters of substrate, which was in this case 10 micromolar L-dopa stock solution, was added to each tube. Incubated at 13 Celsius for 9 minutes this time with gentle shaking. We made sample blanks as well as reagent blanks. Sample blanks with peat and milky water in place of L-dopa. And then the reagent blanks, we used 190 microliters each of milky water and L-dopa stock. All of the peat-containing tubes were centrifuged at 10,000 RPM for 10 minutes. And then 380 microliters of supernatant was pipetted into microplate wells and analyzed at 460 nanometers. And these also, everything was done in triplicate at least. The hydrolase assay was similar, but we used the fluorescent substrate methyl umbelliferol to quantify the activity. As in the phenol oxidase assay, 500 microliter aliquots were taken from each sample and homogenized, placed in pre-weighted Eppendorfs. And we used 5 different specific hydrolase substrates: phosphate, N-acetyl beta, D-glucosamine, sulfate, beta D, xylopyroxide, know the Finnish accents now, and glucoside. The tubes were vortexed and allowed to react at 13 Celsius for 60 minutes. With the exception of the phosphatase samples, that was only 45 with gentle shaking. Centrifuged at 10,000 RPM for 10 minutes again. 380 microliters of supernatant were pipetted into the UV microplate wells in triplicate. We used the free acid solution to create a standard curve for each substrate in 0, 5, 50, 100, and 250 micromolar dilutions. And this time, the fluorescence was analyzed in the fluorostar, excited at 330 nanometers, and emission was measured at 450. So for the quantification of greenhouse gas evolution, we took 10 milliliter water samples into 60 milliliter syringes fitted with three-way stop cocks here. And then they were acidified carefully with 1 ml of 0.1 molar sulfuric acid. And 50 milliliters of diatomic nitrogen gas were drawn into the syringes and shaken vigorously by hand and then in a shaker for 5 minutes. And this basically elutes any dissolved gases into the nitrogen gas. So we can take the nitrogen gas samples, roughly 40 milliliters, from syringes into nitrogen flushed 6 milliliter glass vials for analysis using the gas chromatograph. And this courtesy picture of Joan Carreres. Accent now is getting Spanish, but Joan was really helpful to me in doing this very work-intensive assay. And then our results. Phenolics here. You can see that there was not a ton of difference between Sphagnum treatment and the phenolics, but there was some difference between layers. So older peat tended to show lower phenolic content, whereas upper had greater phenolic content. The phenolics versus the pH, there was a weak correlation here. As the pH gets higher, you have lower phenol content, which is kind of expectable because phenolics themselves are acidic, but it is probably more likely due to the functionality of phenol oxidase, which had a clear correlation with the Sphagnum treatment. So it was interesting to find that it seemed to work the opposite way in the chambers that did not have Sphagnum cover over top. So the upper layer here showed more phenol oxidase activity than the lower layer here, very much opposite in Sphagnum treatment. And there was also some correlation between phenol oxidase activity and redox potential that differed a bit between the two treatments, Sphagnum or no Sphagnum treatment, denoted here water. Hydrolase activity gave us a really clear layer effect as well. So the older peat layers, the lower layer here shown in green, showed a much higher hydrolase activity, which is not terribly surprising because hydrolases can function in hypoxia. So phenol oxidase is very much dependent on oxygen presence. Hydrolases can function without it, so the deeper peat layers that at least previously had existed without oxygen should have these processes going on anyway. These are also required to degrade the material that is present in deeper peat layers. So it is expectable, but really gave us a much more clear demonstration. And this is the last two hydrolases. Again, clear layer effect with the one exception of MUF-X. Everything else showed us that the lower layers seem to have much higher hydrolytic enzyme activity. And then here, the hydrolase is correlated with phenolic activity, or phenolic content rather. So there was a negative correlation. As we have more phenolics in the environment, we have lower hydrolase activity. And that is interesting in the phenolic latch hypothesis because the more phenolics that are in the environment, the lower, this is congruent, I should say, with the phenolic latch hypothesis. The more phenolic content in the environment, the less effective hydrolases are at degrading organic material, and therefore the lower greenhouse gas emission from that environment. And then methane and carbon dioxide. Really clear, slightly strange result. We had almost zero, effectively zero methane content in the water samples with no Sphagnum cover. And a fair amount of accumulation in the Sphagnum treated samples, and significantly more here in the upper layer. The same in the water samples looked at our methane. This is carbon very, very low in the no sphagnum samples. A lot of accumulation here in the sphagnum treated samples. To revisit the hypothesis, phenol content didn't really differ between sphagnum treatments, so hypothesis 1 is a little bit difficult to assess. It's evident that phenolics will inhibit hydrolase activity, but I personally wonder if we had enough time to really analyze the amount of phenolic, or rather the amount of influence that sphagnum cover will have on phenolics. So I think with time, we would see more phenolic activity or more phenolic exudation by sphagnum if these samples were incubated longer. There was apparent promotion of phenol oxidase by phenolic content themselves, which supported our hypothesis 2, the priming effect. The phenolic inhibition of hydrolytic activity was also quite clear. So there was phenolic. Usually enzymes are negatively correlated with their substrates. In this case, we had positive correlation between the enzyme and the substrate, which is unusual. So that's something to be considered. And the conclusions are also a little mixed regarding hypothesis 3 that sphagnum will physically block gas exchange and reduce redox potential and oxidative activity, which should inhibit the decomposition chain. We had higher redox ratings alongside the accumulated greenhouse gases in the sphagnum treated samples, so that complicates things. Sphagnum plus chambers that have the floating sphagnum mat could have simply maintained the concentration of greenhouse gases or just the material that evolves greenhouse gases that was already present in the water column. It could have contributed to their evolution by this priming effect, or it could be a combination of these factors plus other factors we're not sure about. That one requires some thought and some more evaluation, I think. Phenolics, again, did not vary substantially between the sphagnum treatment or no sphagnum treatment, but under both treatment conditions, it was notably higher in the newer peat samples. So that means newer peat has accumulated phenol recently and have not yet been degraded. Positively correlated with phenol oxidase readings. So is that evidence of a priming effect? Is the production of phenol oxidase itself stimulated by phenolic presence? That's another question. And there's a negative correlation with pH, which is expectable. The use of L-DOPA as well has been criticized as a substrate for peatland phenolics assays because L-DOPA requires a pH of almost 9 to be effective, which is much, much higher than acidic peat environments. So maybe it's not representative of natural conditions. That was one paper I had referenced in my thesis because that's something to take into account when interpreting our results. Phenol oxidase, sphagnum treatment stimulated phenol oxidase activity, and the positive correlation with phenol indicates that the production is not yet sufficient to adequately consume all of the phenolics in the environment exuded by sphagnum. Redox measurements are also higher in the sphagnum plus treatments. Not expected, but necessary for oxygen-dependent enzyme activity. And especially in the light of phenol oxidase, our results do not fit the simplified phenolic latch hypothesis. So I think that means the phenolic latch hypothesis just isn't that simple. It's a more complicated process than we have thought previously. The sphagnum minus samples seem to show oxidative stimulation of phenol oxidase in the upper layers. Findings in the sphagnum treatment samples show the opposite, which is perhaps a consequence of phenolic leaches in the water column having an effect on the pH. And that, of course, will alter any enzymatic activity. Enzymes have their optimal pH levels at which they function. So maybe it's just altering functionality like that. Because our samples were taken, again, from an ecosystem in transition, inconsistencies with literature is expectable. This ancient hypoxic peat is suddenly exposed to oxygen, to liquid water, and to aerobic microbial degradation as opposed to simply anaerobic. So there are a lot of other factors to be considered. With hydrolases, there was no clear effect of the sphagnum yet. I wonder if this will increase with time, because there was a clear negative correlation between phenolic concentrations and hydrolytic activity. So if sphagnum continues to colonize these thermokarst pools and exude sphagnum into the water column, that will probably inhibit hydrolase activity if phenol oxidase still is not sufficient to consume all the phenol or phenolics in the environment. So the results here, at least, are incongruent with previous research showing that phenolics inhibit hydrolytic enzyme activity. This was higher in chambers that contained older peat as well. Again, that's expected. Hydrolysis can function without oxygen and can catalyze the degradation of more complex carbohydrates, aromatics, humic material. The possibility of hydrolytics being functional if the phenolic oxidation continues, it would be good for climate change if hydrolytics were inhibited. Simplified again, that's not the only answer, but if the environmental capacity to oxidize phenolics is, if phenolics are able to be oxidized, hydrolysis is able to act, and that gives us more greenhouse gas evolution. And then for methane and carbon dioxide, the near complete absence of both gases in the water columns of all the sphagnum minus sample chambers was kind of striking. The sphagnum mat formation, we're pretty sure this did physically block gas exchange between the thermokarst water and the atmosphere. Redox was higher in sphagnum plus, and that was not expected. But it looks like the clamming effect as a result of chemical change or microbial community is probable. Emission of carbon dioxide has been shown in the literature to increase with phenolic concentration. So the organic chemistry here does exhibit strong controls on carbon dioxide release. The opposite is true for methane. There's no documented controls on peat organic chemistry on methane emission. It looks like water logging is the main driver. So as peatlands are inundated with water where they were not previously, it's shown to increase methane evolution. However, most of the literature that I've studied on this shows this more in a ditching and then re-wetting event. So peatland restoration, this has been shown to happen. Most of that was not done in these Arctic ecosystems, so it could work differently. There's not much that has been done on this topic anyway, in terms of Arctic pulsamiers. And then to conclude, the future of Arctic pulsamier ecosystems, sphagnum did certainly alter decomposition chain exoenzymes to some extent. Peat quality had effect, certainly, and in every case, sphagnum addition stimulated the decomposition chain and promoted methane production. Negative correlation between hydrolytic enzyme activity and phenolics were interesting, but not definitely relatable to sphagnum treatment. The research partially supports the enzymatic latch hypothesis, with further studies in the field, I think, required to better understand these complex dynamics. Questions remain about the long-term consequences of changes in peatland biodiversity and what biodiversity will do regarding their future efficacy as a global carbon sink. The process of pulsamier recharacterization is, of course, synonymous with the transformation of these environments into something else. Bog-type habitats, they're already critically endangered, so that really means the extinction of a whole ecosystem type. And that, I think, is detrimental when it comes to climate change, as these are an important carbon sink. So I would suggest that efforts are made to protect all remaining pulsamier ecosystems from further disruption. And I'd like to thank Dr. Teemu Taapanainen for all of your academic support, and Maija Marshak from Kuopio, who has been my co-supervisor here. Our colleagues at Ohio University, who were very helpful to me in gathering my field samples, as well as our PhD researcher here, Leo Vainio, and at Hokkaido, Joan Isora, as well as my colleague Joan Carreres Calabuig, for helping me so much with those enzyme assays and everything else. Rose Asgard for helping me with the monitoring experiments, and the University of Eastern Finland as a whole. I'm really grateful to have had the opportunity to do my master's research here. It's truly been a joy. Kiitoksia, gracias, shukran, shukriya, nandri. Thank you, everybody.
Many details to this.
Yes.
Yeah. Okay. Thank you, Rebecca, for the nice presentation. So even though I look at that your presentation, I have some clarification and things. Let me ask few questions so to make sure my understanding. So first I will start from the introduction part. You mentioned about something like the first my question is about you mentioned the thermo and hydrological fluctuation influence the peat plant chemistry. So
Yes.
how does it influence? Can you explain a little bit?
Certainly. Let me go back to my...
The introduction part, I think the slide introduction part. Maybe
Yes, I'll pull up.
6 or so, something like 8. Before the chemistry.
Do you want me to... I can
Okay.
explain it with this
Okay.
little graph here. So, you wanted to ask about both thermal and hydrological
Yeah,
fluctuation.
function, yeah.
Okay. First of all, actually, no, my image somewhere over here